This 6.1 video is on radial density. And radial density is the idea that as you move away from some kind of epicenter, that the number of items that you are concerned with will be less and less. So you have some kind of epicenter at the middle, something of importance, some kind of resource, and then the amount of that resource, be it maybe a population that it affects, as it grows from that center, becomes less and less and less of interest. So maybe this is kind of an issue with like a patient 0 in the middle, and the farther out from patient 0 you get, the less likely you are to find the virus. Let's say there's a popular restaurant in the middle, and the likelihood of you finding somebody with a wrapper or a mint or a napkin from that restaurant gets less and less likely the farther away you get from that popular restaurant. Let's say it's a hot day and there's an ice cream shop, and the farther away you get from that ice cream shop, the less likely you are to find somebody with a cone of ice cream. So this idea that radial density kind of moves away as you get farther and farther out. What these circles are actually concentric circles. So that is to say that I've drawn them so you could see kind of like the radii of the circles, but really, I'll draw them in gray. They're filled in, like so it doesn't look like anything. All you've got in the middle is this thing, whatever is important. And then depending on what area of that circle I've picked, and it can be any, and that area of the circle, depending on what ring I'm choosing, that there I can measure a density. And just like with Riemann sums, the actual density in there is really, really narrow. I mean, it's just, oh, there's density. That ring has a density, and even that's too thick. The thickness of that any given density is infinitesimally small. And within that density, within that ring, there might be multiple organisms of whatever my concern and question. So what's really happening here is we have a radius from the center to that outside thing, whatever I'm interested in. And that outside thing is kind of a shell that is around. Think of it like rings on a trunk. It's a shell, a tree trunk. It's a shell of stuff. And within that shell of stuff has whatever we're interested in. But that shell is actually the circumference. So it can be measured at 2 pi r. So given that PR is a function of population density, with R equaling radius from center, the total population from center to outer shell. So in this picture that I've drawn here, from here, all the population that lives in that area. Get my gray back out, because everything around it, can't draw it, so everything around that circle is not included. I'm concerned with what's in the pink. What's in the pink right there? The total population that lives inside that pink zone can actually be written as an infinite sum from the center to the edge of the radius of all the circumferences times that radial function with respect to r. So I'll repeat. Everything that lives in the pink can be written as an infinite sum of the circumferences with those concentric circles surrounding that center piece, and all those circles add together however many times you need to draw it, in an infinite sum from the center to the edge. And then you multiply how many circles you have basically there, how many circumferences and the size of each circumference by the density function, or the how much stuff is in a given area with respect to r. So let's say we have some gorillas and their radial density in a given area surrounding some water source is equal to 10 times 1 plus r to the negative 2. And that's the number of gorillas per kilometer square. And r is the distance from grassy area with food and water. We want to find number of gorillas in 5 kilometer area. So to do that, we're going to go ahead and integrate 2 pi r times 10, 1 plus r to the negative 2 dr. I need some bounds, so I'm going to start in the center, and I'm going to go to the edge of the radial that I'm concerned with. So let me clean this up. I'm going to take the 2 and the 10 out, so I get 20, still 0 to 5. Oop, 20 pi. I can take that pi out too. And I have r, 1 plus r to the negative 2 dr. So now we need to integrate this. To do that, I need to do a u sub. U equals 1 plus r, so that r equals u minus 1. Du equals dr, thankfully, mercifully. So, shrinking that down because I need some more space. This can be written as 20 pi integral of. Change those bounds, so that looks like it's 1 to 6 now by plugging it in here. 0 plus 1 is 1. 1 plus 5 is 6. So 0 goes to 1, 5 goes to 6. R is 1 plus, or excuse me, I wrote that wrong. R, right here, is u minus 1. And 1 plus r is now u to the negative 2, du. So 20 pi, 1 to 6, u to the negative 1 minus u to the negative 2, du. 20 pi is ln of u minus u to the negative 1 over negative 1, all from 1 to 6. So, put parentheses, whoops, apologize. Okay. 20 parentheses, 20 pi ln of 6 plus 1/6 minus ln of 1 plus 1 equals 20 over pi, that's 0, ln of 6, that minus combines with that positive to make a negative, so negative 5/6. And I get an answer of 60.22, which you can't have 0.22 of a gorilla, so depending on my error, I have somewhere between 60 to 61 gorillas in the mist, which is an old movie.